in the contemporary PC industry. Nowadays, the PCI interface is gradually expulsed by a more productive interface. Modern mother plates are provided with only one or sometimes two PCI slots instead of 5 or 6 as it was made.
For the past decade, PCI technology has served as a ubiquitous I/O interconnect solution for computing platforms. First introduced in 1992, PCI is based on a parallel bus model with initial connectivity of 32 parallel signals operating at 33 MHz. In order to scale performance with computing requirements, the industry has either increased the number of signals or increased the signal frequency. After a decade of improvements, however, the parallel PCI model is reaching its limits, making further performance enhancements expensive, less reliable, and more complex while restricting design flexibility in delivering PCI connectivity. Here we see the effects of signal skew versus clocking due to increased frequency. Increasing the number of signals further exacerbates clocking issues by augmenting the number of signals that must be synchronized with the common clock. A new alternative for I/O connectivity is required. PCI Express technology has been developed by the industry to address the needs for the next decade's computing and communications I/O requirements. Based on a serial model, clocking data at 2.5 GHz via two differentially signaled half-duplex lane pairs of wire, PCI Express technology addresses the fundamental issue of performance scaling by encoding clock and data into a single stream utilizing SerDes silicon. As a result, we are able to increase signaling speed significantly while dramatically reducing the number of signals. The resulting reduction in pin count increases design flexibility while creating more efficient and cost-effective I/O solutions. PCI Express technology was designed to utilize the extensive industry investment in software development by featuring backward software compatibility with legacy PCI infrastructure. PCI Express architecture will be used in a wide range of design platforms as a chip-to-chip and chip-to-adapter technology. Desktop and notebook designs will utilize PCI Express slots and connectors, along with Express card modules to deliver efficient connectivity solutions and true plug-and-play capability. These benefits are offered while simultaneously enabling an enhanced graphics performance roadmap and the transition to Gigabit Ethernet. By scaling the number or width of links, PCI Express technology can scale performance to enterprise requirements. The PCI Express specification enables multiple link widths, or presumably up to 80 gigabits per second of link performance at a 2.5 gigabit per second signaling rate, and can be further enhanced through signaling rate increases. Scaling width and frequency within a serial infrastructure does not have the same limitations as discussed in a parallel model due to each signal containing encoded clock and data. Servers are expected to utilize PCI Express technology via slots, server modules, and motherboard implementations. Next-generation modules and motherboard configurations deliver new flexibility in server motherboard design, aiding in delivery of dense rack mount and blade servers. By matching the performance requirements of 10 gigabit per second interconnects, PCI Express technology enables balanced server platforms, freeing processing power from traditional I/O bottlenecks. PCI Express technology also extends PCI's role in the communications industry. Within an internet infrastructure, PCI Express technology will be found embedded in traditional communications applications as well as extended into new interconnect uses. Initial PCI Express implementations will transition PCI-based connections to the higher performance and lower pin count offered by PCI Express designs. The industry is moving forward to PCI Express solutions.
RAM or random access memory is temporary memory, and it's installed on the motherboard in the memory slots. A motherboard can have a various number of memory slots. The average motherboard will have between 2 and 4 of them. Memory slots come in different types, depending upon what type of RAM it accepts. For example, most motherboards have DIMM memory modules because it's the most common type to date. DIMM stands for Dual Inline Memory Module. A DIMM memory module has either 168, 184, or 240 pins. A DIMM is a dual inline module because it has 2 independent rows of these pins, one on each side. And DIMMs have a 64-bit data path. Another type of memory module is a SIMM. SIMM stands for Single Inline Memory Module. A SIMM is an older technology and has since been replaced by the much faster DIMM. A SIMM also has pins on both sides like a DIMM, but in a SIMM, the pins are redundant, compared to a DIMM, which are independent. A SIMM will either have 32 or 72 pins, and a 32-bit data path. Another type of memory module is called RAM, which stands for Rambus Inline Memory Module, which was developed by the company Rambus Inc. RIMs have 184 pins and look similar to a DIMM, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. Now the term 32 or 64-bit data path refers to the number of bits of data that are transferred in one cycle. The more bits that are transferred in one cycle, then the faster the computer will be. A single bit or 1 bit of data is the smallest form of data that a computer reads, because in the computing world, a computer only understands ones and zeros, which is represented by a single bit of data. Now there's also the term byte, and 8 bits is equal to 1 byte. So if a memory DIMM is rated to have a 64-bit data path, then that means that it has an 8-byte wide data path or bus, because 64 divided by 8 equals 8. And if a memory SIMM that is rated to have a 32-bit data path, then that means that it has a 4-byte wide bus, because 32 divided by 8 equals 4. So that's why DIMMs are faster than SIMMs. Now this information will be useful in an upcoming lesson on how we determine the exact bandwidth of memory modules. In section 1, we talked about secondary memory, which is permanent storage. This dealt with hard drives. Now we'll talk about primary memory, or temporary storage. This is called RAM. RAM stands for Random Access Memory. In order for data or a program to run, it needs to be loaded into RAM first. So here is how it works. The data or program is stored on the hard drive. Then from the hard drive, it is loaded into RAM. And once it's loaded into RAM, the CPU can now access the data or run the program. Now, a lot of times, if the memory is too low, it might not be able to hold all the data that the CPU needs. And when this happens, then some of the data has to be kept on the hard drive to compensate for low memory. So instead of data going from RAM to the CPU, it has to do extra work by going back to the hard drive. And when this happens, it slows down the computer. So to solve this problem, all you need to do is increase the amount of RAM on the computer. And by increasing the memory, all the data can be loaded into RAM without the need of constantly accessing the hard drive. and the result is a faster performing computer. RAM requires constant electrical power to store data, and if the power is turned off, then the data is erased. RAM is stored on the motherboard in modules called DIMMs. These DIMMs come in different memory sizes. Today, they range anywhere from 128 megs to 4 gigs of memory per DIMM or more. RAM also comes in different types, such as dynamic RAM or DRAM. DRAM is memory that contains capacitors, and because it has capacitors, it has to be refreshed often. SRAM stands for synchronous RAM. This memory uses transistors and does not have to be refreshed, unlike DRAM. And because of this, it is much faster than DRAM, and it is also very expensive. An example of SRAM would be the memory cache level 1 and 2 that is used by the CPU. Another type of memory is called SDRAM, which stands for synchronous DRAM. This type of memory is what is used today in RAM DIMMs. The difference between SDRAM and DRAM is basically speed. The older DRAM technology operates asynchronously with the system clock, which basically means that it runs slower than the system clock because its signals are not coordinated with it. But SDRAM runs in sync with the system clock, which is why it is faster than DRAM. All the signals are tied to the system clock for a better controlled timing. SDRAM is rated at different speeds. For example, a stick of SDRAM could be labeled PC100. The 100 equals the speed at which it operates, which is 100 megahertz. And since SDRAM only comes in 64-bit modules, it has an 8-byte wide bus, because 64 divided by 8 equals 8. So to figure out the total bandwidth of PC100, you multiply 100 megahertz times 8 bytes, which equals 800 megabytes per second. So the total bandwidth of PC100 equals 800 megabytes per second. So an SDRAM module labeled PC133, you multiply 133 by 8 bytes, which equals 1066. So the total bandwidth for PC133 equals 1066 megabytes per second. As technology increased and processor and bus speeds have gotten faster, a new RAM technology was developed to keep up with the faster speeds of computers. This newer technology was called DDR, which stands for double data rate. And that's basically what DDR does. It sends double the amount of data in each clock signal when compared to non-DDR RAM. Non-DDR or single data rate RAM uses only the rising edge of the signal to transfer data. But DDR uses both the rising and falling edges of the clock signal to send data, which makes DDR twice as fast. DDR is also labeled differently than non-DDR RAM. Instead of including the clock speed in its name, like PC133, where 133 equals the clock speed, DDR uses the total bandwidth instead. For example, a DDR DIMM labeled PC2700. The 2700 is not the clock speed, but it's the actual total bandwidth. The clock speed for PC2700 is 333 megahertz. So 333 megahertz times 8 bytes is rounded off to 2700 megabytes per second, which is where we get the name PC2700. Another example is PC3200. PC3200 has a clock speed of 400 megahertz, so 400 times 8 equals 3200, which is where we get the name PC3200. A new technology that has succeeded DDR is DDR2. DDR2 is faster than DDR because it allows for higher bus speeds, and it also uses less power than DDR. A DDR2 DIMM has 240 pins, compared to 184 pins on DDR. Some examples of DDR2 are PC2 3200 and PC2 4200. And the latest RAM technology is called DDR3. DDR3 is twice as fast as DDR2, with a bandwidth of over 12,800 megabytes per second. Like DDR2, a DDR3 DIMM also has 240 pins, but the notches in the DIMMs are in different places. So you can't put a DDR3 DIMM in a RAM slot made for DDR2. In fact, motherboards are made to support a certain type of memory, so you can't mix DDR1, 2, or 3 on the same motherboard. Some examples of DDR3 are PC3 8500 and PC3 12800. Another type of memory was called RDRAM, which was developed by Rambus Inc. And they developed the RIM, which stands for Rambus Inline Memory Module. RIMs have 184 pins and look similar to DIMMs, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. When RDRAM debuted in 1999, it ran at 800 MHz, which was considerably faster than SDRAM, which ran at 133 MHz at that time. But even though it was a lot faster than SDRAM, RDRAM only had a 2-byte wide bus, compared to SDRAM, which had an 8-byte wide bus. So if you multiply the speed of RDRAM, which was 800 MHz, times the bus width, which was 2 bytes, you would get a total bandwidth of 1600 megabytes per second. RIM technology was designed to work with a continuous signal, which means that all the other memory slots on the motherboard must be used for RIMs to work properly. And if other RIMs are not available, then a user can install a CRIM or continuity RIM, which is basically a dummy RIM to ensure continuity in all the memory slots. To meet the higher demands of faster processors and memory controllers, a new technology was developed called dual-channel mode. Dual-channel mode requires a pair of identical DIMMs installed on the motherboard, which allows the memory controller the ability to communicate with 2 DIMMs simultaneously, which increases the speed of accessing the memory. In order for dual channel to work, the motherboard must be equipped to work in dual channel mode, and the memory DIMMs must be identical to each other in speed, size, and features. Then the DIMMs must be inserted into the motherboard in a specific slot configuration in order to enable dual-channel mode. Typically, the memory slots will be color-coded to help assist in identifying where the DIMMs should be inserted. For example, here we have some dual-channel memory slots. So in order for dual-channel to work, you need to install a pair of identical DIMMs in the slots of the same color. In this case, we put a pair of DIMMs in the yellow slots. Some RAM modules have ECC, which stands for Error Correcting Code. And what this does is that it detects if the data was correctly processed by the memory module, and makes a correction if it needs to. You can tell if a RAM module has ECC by counting the number of memory chips on the module. In a standard non-ECC DIMM, it will have 8 memory chips, but in an ECC module, it will have 9 memory chips. Most RAM modules today are non-ECC, and this is because of the advance in technology that has minimized memory errors and has made non-ECC RAM more stable. Typically today, ECC memory is mostly used in servers because servers need to be up and running at all times, and using ECC memory is just an extra precaution to guard against